Hi Saints, this is Mr. Matthew Lim. Today I'll be delivering the third lecture on gravitational field. Today we will focus on two new objectives G and H and revisit an old objective J because we have not spoken about the applications of geostationary orbit. Without further ado, let's look at the next section, work example 9. Right. Explain why geostationary satellite must be above the equator. Now, I'd like you to look at the diagram. I've indicated here three orbits, and I will call this orbit 1, 2, 3. 1, 2, and 3. So to understand why geostationary satellite must be above the equator, we will look at the first orbit. The first orbit is the geostationary orbit, which is orbit 1. And if you look at orbit 1, the center of the orbit coincides with the center of the Earth. And this is the condition for a stable orbit. So, and the geostationary orbit uh, is one where a satellite on it actually appears above a certain point on the Earth's surface all the time as the Earth rotates. Now look at the second orbit. Second orbit is a stable orbit, but it is not geostationary because if a satellite is on the second orbit, it will actually move from one hemisphere to the other hemisphere. Look at this. It will move from the southern hemisphere to the northern hemisphere and then back to the southern hemisphere. So second orbit is a stable orbit because the center of the orbit coincide with the center of the Earth. Now we are going to look at the third orbit. The third orbit is what we call unstable orbit because the center of the orbit does not coincide with the center of the Earth. So for such a case, the gravitational force still points towards the center of the Earth, and that generates two components, the y component of the force and the x component of the force. The x component of the force provides the centripetal force for this impossible orbit, and the y component actually shifts it towards the equatorial plane. So orbit number 3 is an imaginary orbit. It is not possible to have an orbit like that. However, orbit 1 and 2 are possible, even though orbit 2 is not a geostationary orbit. Okay, we are going to make a comparison between geostationary and polar satellite. But before that, I have to show you a video to illustrate what a polar satellite is. Okay, let's look at this video. The satellite actually moves from pole to pole, from North Pole to South Pole, and then back to North Pole as the Earth rotates from west to east. In this case, you see that the satellite is able to scan through every point on Earth because of the nature of the rotation of the satellite. Okay, it goes from North Pole to South Pole, whereas the Earth is moving from west to east, so it is able to cover the whole Earth. Right, let's go back to our lecture notes. Um, Okay, we are going to compare geostationary satellite with polar satellite. Geostationary satellite is much higher. So take note of this. The altitude is much higher than that of polar satellite. Okay, what are the advantages and disadvantages of geostationary satellite? Well, since it is at a high altitude, it's able to view a large area of the earth. Okay, that is the advantage, and it is always constantly above a certain point on the earth's surface as the earth rotates, so it has a constant view of that particular area. Now, what are the disadvantages? Now, because of the high altitude, the resolution of the data is not as high. In other words, we say that whatever, whatever data we get um, is less detailed, okay, compared to later on compared to polar orbit satellite. So even though it views a larger area with less detail, all right. Um, what about this? Polar images are distorted. Polar images distorted because of low angle. Let's look at the geostationary satellite here. Okay, if a geostationary satellite try to view the pole, you'll find that the angle to the surface is actually very small. So the area of the pole as viewed by the geostationary satellite is distorted, right? So let's compare um, the advantages of geostationary satellite with the polar satellite. Polar satellite, you already know, is lower, right? Because it is actually at a lower altitude, and therefore it will have a higher resolution. It will be able to get a greater detail. And just now we already know that this satellite actually moved from North Pole to South Pole and then back to North Pole. The orbit of rotation is roughly about 90 degrees to the rotation of the Earth, and therefore in this way the satellite is able to cover every point on Earth. What is the disadvantage? It cannot provide continuous viewing of one location because it is constantly moving with respect to ground. So it is unlike geostationary satellite, which is always above a certain point on the ground. Okay, so this is the disadvantage of polar satellite. More importantly, you have to focus on the users of the satellite. This is the important part of the comparison. Um, you must know that geostationary satellite is actually used to monitor local weather events, telecommunications, satellite navigation system. You heard about the GPS, okay? GPS, GPS system for vehicles. So it's using the geostationary satellite to do that. For polar satellite, we use it to monitor weather, spying other countries, and study the Earth's atmosphere, right? Okay, next, binary stars. Now, what are binary stars? Binary stars are actually twin stars, and the two stars need not necessarily be of the same mass. So if I call one M1, the other M2, they are not necessarily of the same mass. And because of that, when they rotate about a certain center of mass. Okay, so you may call this the center of gravity. At this level, it is okay to think of center of mass as the center of gravity of the system. So the satellite actually moves around the center of mass. So there is actually a mutual attraction between these two stars. Well, I shouldn't be saying satellite. I should be saying binary stars. Okay, these two uh, stars are actually moving around the center of mass. Okay, so they experience the same centripetal force. Okay, so when we apply Newton's law of gravitation, take note, um, R is actually the separation. R is the separation between the two stars. Okay, and then you equate this to the centripetal force on each star. And you wonder whether why this is possible. Well, although R1 is actually less than R2. Okay, look at the diagram. It simply means that M1 now must be more than M2. So that would balance out. Okay, they have the same omega. Take note, they have the same omega. So if R1 is less than R2, M1 must be more than M2. Okay, so this is the binary star system. So we are going to look at a problem to strengthen our concept here. Okay, I have a binary star system. Okay, but this time both are of the same mass, right? So they both have the same mass. And like before, because the two masses attract each other, they actually each experience a force F. And force F is actually the centripetal force. So we equate it to the centripetal force, okay, mr omega squared, but this time r is half the separation, okay. Take note of these two r. This r is the separation. This r over 2 is the radius of rotation. So you will probably have to pause this video to understand the mathematics, to discover for yourself how you get the answer B. Okay. Now I'm going to move on to something more challenging called the gravitational potential. Look at this gravitational potential. This is something challenging but manageable. Before I explain what gravitational potential is, I want to connect this to your previous knowledge on gravitational potential energy. Okay, at O level, this is what you learn. Huh? Wait, at O level, this is what you learn. At O level, you learn this. That is, at the Earth's surface, you take the gravitational potential energy to be zero. Okay, you take the GPE to be zero. And then as the body goes upwards from the surface of the Earth, the body has positive gravitational potential energy. You can see that the value is increasing, right? Value is increasing as you go higher and higher from the surface of the Earth. Okay, let's look at A level. We are going to separate this, right? At A level, we are using the negative scale, okay? So this is the challenging part because many students has difficulty adapting to the negative scale. This time, the zero is not uh, assigned at the Earth's surface. So zero GPE is now at infinity. You can see that this zero GPE, okay? So GPE at infinity is now assigned zero. So the reference point for zero GPE is now changed from Earth to infinity, right? And then notice that as you go towards the Earth, all the values of GPEs are negative, okay? All other values of GP are negative values. So at A level, we are going to adapt to this system. And why are we doing that? That's because of the definition that we will see later on. Okay, so I want you to see that for both scale, as you move upwards, the value of GPE is getting bigger. Take note that minus 10 is more than minus 40. Okay, so as you go higher and higher up, the GP value is getting bigger. Less negative means a bigger value. Okay, so I would like you to probably take a snapshot of this so that you can understand that we are going to use the negative scale for GP. Now I'm going to link this concept to gravitational potential. What is actually gravitational potential? This is what you are going to learn today. Gravitational potential phi is basically the gravitational potential energy per unit mass. All right, remember this. So this is the idea or the connection between gravitational potential and gravitational potential energy. Let me say it again. Gravitational potential phi is actually gravitational potential energy per unit mass. So this is the idea, the big picture I give you. Now, the definition of gravitational potential is actually very special. Okay, let's look at this statement. Gravitational potential phi at a point in a gravitational field is defined as the work done per unit mass in bringing a small test mass from infinity to that point without a change in Ke. So this is infinity. All right, I call this point infinity. At infinity, I have a body here and I bring this body here. I'm talking about mass m. So this is mass m. I bring it from infinity to that point. Now, if you look very carefully, um, there is an external force here which is provided by an imaginary giant. And why do we need this external force? Now, here there is a force of attraction. If you look at here, there's a force of attraction Fg, force of attraction between the Earth and mass m. Okay, so these two forces are what we call the equal and opposite reaction, action and reaction. Okay, now without the external force, I'm going to highlight the external force in green. Without this external force, this body will accelerate towards the Earth and then crash it at the surface. Okay, crash at the surface. We don't want this to happen. Okay, in the definition of gravitational potential, we actually bring the body from infinity to point P. This is point P. Okay, this point P. So I bring it from infinity to point P without any increase in the kinetic energy. So I need a force external. Force external is a restraining force. Okay, the restraining force prevents the body from accelerating. So restraining force is theoretically equal and opposite to Fg. Okay, so that is why um, the idea seems to be quite strange to many of you, because you are actually bringing a body from infinity, which is a remote place, somewhere very, very far away. Okay, and I want you to know that the work done here is actually a negative work done, because as you move in this direction, okay, so this is the displacement x. So can you see that x and F external are opposite in direction? Can you see these two are in opposite direction? Okay, can you see this direction and this direction? They are opposite in direction. So from chapter 5 WEP, if the force and the displacement are in the opposite direction, then the work done is a negative work done. Okay, so let's look at the explanation of gravitational potential here. So we are aware that mass m is experiencing an attractive force exerted by mass big M. Okay, so as you bring mass m from infinity to point P without any change in Ke, the external force which is provided by the imaginary giant is actually opposite to the direction of the pull of gravity, and it uh, is also opposite to the displacement, right? So because of that, the displacement and the force are opposite, so the work done is negative. Okay, work done is negative. So since GPE is zero by convention, that is at infinity, GP is zero. So in this case, GPE is zero at infinity. So let me write down by convention. Okay, just now we already know that we define at infinity GP is zero. So the potential at infinity is also zero. So it's by definition, potential at infinity is zero. So therefore, what is the potential at P? Potential at P. Potential at P is very simple. You just take the negative work done plus the potential at infinity. This one comes from here, okay? So the negative work done plus zero, you still get a negative value. So the potential value is always negative because of the negative work done. So negative work done plus a zero value, you get a negative potential at P. So that is why work done per unit mass from infinity to point P is actually defined as gravitational potential. Okay, so you have to get used to this idea that gravitational potential energy per unit mass is actually the potential, gravitational potential, right? So let's move on. Now, here you have a chunk of mathematics. Let me suggest this to you. They are actually not really needed for A level. So if you like, you can look at it. If not, you can forget about it. Okay, this one is not important. What is important is this equation. Look at this equation. You have to memorize this equation. Remember, equation 7.7. And this is the equation for gravitational potential. Now, I want you to look at this very carefully. This formula contains a quantity called R. Remember, in the definition of gravitational potential, we talk about bringing a unit mass or bringing unit or rather uh, work done in per unit mass in bringing the small test mass from infinity to that point. The displacement is from infinity, but this time when we do our calculation, R is measured from the center of the planet. Okay, we don't we no longer use X. X is the displacement that we use in the definition here. Okay, in this definition, we use X, the displacement. All right, but when we do our calculation, we use R as the reference, measured from the center of the planet. Why is that so? For this very simple reason, we do not know how to measure X because X is actually um, a theoretical concept that we measure from a point called infinity, and that point infinity is not well defined. Okay, so therefore we have to use R instead. So memorize this equation because subsequently we have to apply this equation. All right, gravitational potential, like potential energy, is a scalar. Okay, so it has a unit joules per kg because just now we learned this as work done per unit mass. All right. Okay, I already mentioned to you that a point of infinity is actually a point very far away. It's not very well defined. It's just a point far away. By definition, potential at infinity is zero, same as gravitational potential energy. Um, both of them are zero, all right, at infinity. All right. Potential does not depend on the mass m which is placed in the field, but on the mass m that creates it. Yeah, we know the formula. The formula just now I show you is phi equals to minus gm over r. So it depends on this big M, the mass of the planet that creates it. Okay, so it does not depend on any small mass around it. All right, four. The negative sign must be kept for potential. Yes, because we know it is a negative work done per unit mass. So um, the negative sign is important. And negative sign is also associated with attractive forces. Gravitational forces are attractive forces. The last two may not be that important because number five talk about test mass must be small. It is because if it is big, it will distort the field of the source. Um, so that's the reason. And number six, you may not use it now, so it may not be that important. Number six, so you can put this aside for the time being. Okay, let's look at work example 11. Explain why gravitational potential values are always negative. Oh, just now I've already explained it to you. Let me explain it one more time. Um, uh, okay, potential at infinity is defined as zero. Okay, that's by definition. Okay, at infinity, potential is 0 joules per kg. Okay, so take this as a definition. So we say it here. by definition, it is zero. So between the mass and the planet, there's an attractive force, right? So I've explained this to you just now, but I don't mind explaining it again. So this is the force of gravity, right? Force of gravity. So you have an external force here, which is provided by an imaginary giant. So you are going to bring this body from infinity to that point. Suppose it starts from infinity to this point, and I call this point P. Okay, this point P. So F external is doing a is actually doing a negative work done because um, if it moves the body from infinity in this direction, if x is the displacement, then the direction of x and the direction of F external, they are opposite. So these two are opposite. Can you see the direction are opposite? So opposite direction, you get a negative work done. Okay, so F external provides a restraining force so that mass M will not accelerate and crash onto the surface of Earth. Okay, so uh, therefore the potential at P. So let me erase this one away. So potential at P is actually a negative work done per unit mass plus zero plus the original value, which is zero. This is potential at P. Okay, so therefore, gravitational potential, which is defined as the work done per unit mass in bringing the body from infinity to that point, is negative because the work done is negative. Now, we want to talk about gravitational potential energy. Just now I told you that gravitational potential energy, GPE, is actually the potential, or rather I should say it again. Let me say it again. Gravitational potential is actually the gravitational potential energy per unit mass. Okay, so from now on, we will write GPE as U. We are going to change the symbol to U, okay, for simplistic sake, okay. So GP is U. So now we define gravitational potential energy of a mass in a gravitational field as the work done in bringing that mass from infinity to that point. So I want you to take note, it is not per unit mass, it's bringing that mass. So that is the difference between this definition compared with definition for gravitational potential. Okay, so if I write it like this for this particular equation, so now I can combine this, right? So then you will be able to see that actually GPU is equal to M5. That's how we get the subsequent equation. So you have to memorize this equation, 7.9, which is essentially this one. And then, of course, any change in the potential will cause a change in the gravitational potential energy. So you have to memorize 7.8, 7.9, and just now 7.7. So as you bring the body from infinity to that point, so there is a change in potential, so there's a change in potential energy. So you can see these two values are zero because they are values at infinity. Okay, at infinity, gravitational potential energy is zero, gravitational potential is zero. So as a result, we can derive this. Okay, so whereas this u value is the value at a certain point p, at p. Okay, One of them is at infinity, the other one is at p. So you have four equations here. Can you see you have four equations? Equation 7.8, 7.9, 7.10, and then here I write down for you 7.7. Equation 7.7, which is actually phi equals to minus gm over r. Okay, you have to memorize these four equations. One, two, three, four. Okay, four equations. Memorize these four equations because we are going to apply this again and again. Okay, we are going to apply these four equations starting with equation starting with work example 12. Okay, come to the note. I've already explained it to you all this. Okay, gravitational potential is always negative. GP at infinity is zero. Yeah, all this I already explained it to you, all right? So let's look at example 12. Assuming the Earth is a uniform sphere. You see, at A level, the Earth is most of the time a uniform sphere. So you don't take Earth as bulging at the equator. No, we will take it as a perfect sphere. So with the value of radius and mass given, calculate the gravitational potential at Earth's surface and to a point 600 kilometer above the Earth's surface. So you have to recall this equation. So when you recall this equation, then all you need to do is to substitute the values. Okay, so potential at the Earth's surface, so you use R as measured from the center of the Earth. So if you want work done, or no, the second part, you want the gravitational potentials at a point 600 km above the Earth's surface, then you have to add the altitude to the radius. Okay, and then you need to recall this equation. Recall this equation. You want to find the work done in bringing a 5 kg mass from the Earth's surface to a point 600 meters above the Earth's surface. So we know this. This is the Earth, right? So you want to bring it up from here to a point which is 600 meters. Okay, there's an increase in GPE. Okay, so delta U is actually the increase in GP, delta GP. So get used to the symbol. Delta U means delta GP. So you just take M delta phi, substitute the values uh, for the from the earlier part. This one is phi final. This is phi. Uh, this is phi final. This is phi initial. Okay. Okay. Get it? So you apply this equation, you should be able to get the answer. And the next one, part C, work done in bringing 5 kg mass from Earth's surface to a point where the Earth's gravitational field is negligible, means you are going to bring this from the surface to infinity. Okay, so if you bring it up to infinity, the final value, okay, is zero. The final potential is zero. So eventually you'll get this answer. That's example 12. Example 13 is about changing the height of the satellite. You are going to move the satellite, which is 120 kg, from a lower orbit. This is a lower orbit, 600 or 6,610 km to a higher orbit, okay, radius which is 6890 km. So you are actually moving it from a low orbit to a high orbit. So you need to have a change in the potential energy. So this is change in GPE. Change in GPE. So you substitute the values into the equation. All right. So you probably have to pause the video to see how the mathematics work out to give you this answer. Oops. Okay. So just take note of the common error. This part, delta R is not equal, or this term, 1 over delta R is not equal to this term. They are not equal. Many students make this mistake. This is a common mistake. Take note. Study the mathematics. Pause the video, study the mathematics. Okay, work example 14. Satellite of mass 100 kg moves from a point where the gravitational potential is minus 30, okay, minus 30, to another point where the gravitational potential is minus 60. So just now you remember at infinity, remember if I were to put a scale, I put a scale standing on the surface of the earth, okay, suppose this is a scale, then the potential at infinity potential is zero. Anywhere else the values are negative, right? The values are negative. So you can see that the more negative the value, the nearer it is to the Earth's surface. Okay, so obviously, moving from a potential of minus 30 to minus 60, the body or the satellite is moving closer to the Earth and not further away because it's moving from minus 30 to minus 60. So the question say, calculate the gain or loss. So it's a loss lah. It is a loss. So if you take the final value, which is a smaller value, um, so eventually you are able to get the loss. So what is important here is the formula. You must remember the formula. If you have no, if you don't know this formula, then you cannot solve the change in GP. Okay, the last one is actually not really an example for you to do it. Is actually for you to understand. It's actually FYI, for your information. It is to prove to you that GP is equals to MGH for small h, for small values of h. Okay, when we say small h means h which is less than 1000 meters from the surface of the earth. Okay, 1000 meters from the surface of the earth. So it is just a proof to show you that um, that MGH is only good enough for H value less than 1000 meters. Okay, those of you who are interested in the mathematics, you can actually um, look through the working. All right. So work example 15 is just for your information. So we have come to the end of today's lecture. So it is always good to look at the initial objectives that we have presented to you at the start. Okay, so examine it to see whether you really understand the concept. So that's the end of lecture 3. Thank you very much. Uh, okay, bye.